Hello everyone. Someone in the comment section of my previous video asked me to show you how to or how I implemented my UI system in my engine. And by the way, hello everyone. I'm so sorry for yeah, completely abandoning my channel for over a year, I think. Um, I'm gonna I can make a separate video about that another time, where I answer your questions, because I made a post as well earlier today in the community thing over at YouTube, where I asked you to post some comments of your questions that you want me to answer in a Q&A video. And when I make that Q&A video, I will also explain what I've been doing when I've been off from YouTube. But basically, someone in the comment section asked me to describe how I implemented my UI system in my engine. So I thought I would make a video of this now, but also not only that, but also make a video about how the entire game engine is created, basically. So it's gonna be like a little walkthrough of everything here. So in case you haven't seen the previous video, let me just run the thing here a little bit. This is the demo. I recorded a demo video of this yesterday, I think. It might be a little bit laggy now because in the previous video I was recording the actual window of the game, but now I'm recording the entire screen, so it might be a bit laggy. We'll see. But yeah, here's the game or engine, and it actually has a lot more features than I showed you in that video. So let me show you one thing. For example, actually let me open the settings tab here. So let me go through these settings here. You can see I have a bunch of different settings here. The text might be a little bit small, I'm sorry about that, but here it says debug collisions, debug BVH. You might wonder what BVH is. Well, it's a bounding volume hierarchy structure, and I'm using that for ray tracing, and I'll show you that a little bit later. And here it says live BVH. This is a setting that enables the BVH to be reconstructed every frame. And here's a checkbox for enabling ray tracing. So I'm not actually doing any ray tracing right now. It's a setting that you can enable or disable. And these settings aren't used. This is race only, race colors, debug chunks. So I have this, I have multiple alternatives for acceleration structures in my engine. So you can use BVH or you can use a chunking system like in Minecraft, but the default one is the BVH. And here's the first setting that is actually enabled, and it's SSAO, Screen Space Ambient Occlusion. You can sort of see it around the, if I walk close up to a wall here, you can see there's like it's barely visible, but there's a little, like a dark area around the weapon here. When I'm close to the wall, it's sort of, it looks like the dark area is like a shadow on the wall. And you can sort of see it here as well. It's not actually supposed to be visible here because it's only supposed to be visible when objects are, like for example, near a wall. And what it is, it's emulating how, you know, things would be occluded by some light in real life. So we can turn this on and off, and you'll see the difference. So this is without screen space ambient occlusion. It looks a bit more flat now. So you can see here when the weapon is in front of that box there. If I turn on screen space ambient occlusion, you can see things get a little bit more detailed. Um, and then we also have sun strength. It is what you think it is. We can pump it up a lot and it's gonna look really weird. Actually, let me move my oh, sorry, I had my camera in the way all the time. Let me put it here. And let me show you the ambient occlusion again here. So if we do like that, you can see the difference without ambient occlusion and with ambient occlusion. And where were we? Yeah, sun strength. We also have denoise edge sensitivity. This is really visible for example, on this crowbar here. If I stand here and we turn this off, it might not be visible on the stream here, but things get a little bit more jaggy. So it's sort of like an anti-alias type of thing. Here you can see it on this screen here. The edges are a bit jagged, but if I increase this, things gets a bit smoother. And the other one here is just like a denoising thing overall. It almost blurs the entire screen. But it's actually doing a what it's doing is that it's going through the pixels on the screen and it tries to estimate how noisy a certain area is and blurs that noisy part. For example, it's a bit noisy here, and it sort of blends it out a little bit. And then I have another setting here for material ambient occlusion. So I'm using physics-based rendering, by the way, so it's PBR. And some PBR materials have a property for ambient occlusion, and you can sort of change the intensity of the ambient occlusion here for materials. It's really visible on this thing here. If I increase this to the max, you can see that I don't know, it kind of looks a bit more detailed somehow, but I prefer to have this at 0.4, something like that. And the shadows that you're seeing is just basic shadow mapping. You can turn it off by doing this. So no more shadows. But I have another way of rendering shadows as well, which is a work in progress, but it's ray tracing. So what I can do here is turn on rays. And now we're seeing ray traced shadows. This is a work in progress, as I said. It's not perfect. You can see it's very pixely because I'm actually ray tracing the scene in a separate frame or in a hidden frame buffer on a lower resolution, just to increase performance, basically. And you can see it has some bugs here where, you know, this crowbar shouldn't really be in shadow here. So yeah, it has some problems like that. And also you can see that the shadow of my crowbar is still here from when I turned on ray tracing. And the same goes for if I, for example, move this. The shadow is still there. And this is because I haven't turned on live BVH reconstruction. We can do that. And this is also a work in progress because it's not as fast as I want it to be. So you can see that this shadow will eventually go to where it's supposed to be, but it takes some time for it to do that. You can see the ray trace shadow a little bit better if I turn on the flashlight. You can see that, for example, the shadow of this little building here is cast in real time. And we can also go here, and we should be seeing some shadows here and in the water. And yeah, and also I'm using deferred rendering. That's also another technique that I'm using. And that allows me to do some cool post-processing effects. Like for the water here, you can see that things get a little bit distorted in the background from the waves of the water. Let me actually turn off ray tracing because it's a little bit laggy. Let's turn on that. So you can see here that the ground, it looks like the ground is moving a bit, like it's being refracted by the water. And I'm using this just to, the way I'm doing that is I'm just offsetting the UV coordinates if the camera is seeing something transparent with the material property of liquid. So that's how I'm doing that. And another thing you might noted in the demo I did was that I had some particle effects. For example, I tried to make this smoke particle effect. It's not perfect, but it also has sort of the same technique applied to it as with the water. It's barely noticeable, but you can see that the background sort of gets distorted as if the smoke had some heat to it. So, you know, if you would have like a fire in real life, the background behind the fire would sort of get a little bit distorted. So that's what I'm trying to emulate with this, what I'm doing here. So by using deferred rendering, I can do a lot of cool post-processing effects like that. So that's really neat. And yeah, so that's just another short little demo here. We're gonna go through the code a little bit as well. And what I showed you in the previous video was also this spawn menu here. I think that was what the main question was about, like how I made that thing. But we can, for example, spawn something. Let's spawn a boat maybe. Let me actually fly up a little bit. And I'm going to maybe do the medium one, and let's do disable physics, because otherwise it's gonna lag a little bit. And there we have a boat. So, and by the way, the physics is also something that I programmed myself. I'll show some code of that too. So let's step into the code a little bit. So let's actually start with the what your main question was about, which was the UI. So I have. Let me first say that I didn't initially program this user interface to be used in a game engine or something like that. I was trying to make my own web render or my own custom browser web render thing as a completely separate project. And I did that. The way I did that was that I found specifications online for how elements in a web browser should be positioned and resized based on some rules or some specifications that have been standardized. I don't remember where I found these specifications, but I remember just searching on the internet for like CSS 3.0 specification or something like that, and I found papers from MDN or something where they explained all of the rules that one should be applying when building a web renderer. So the UI is pretty simple. We have this, this is like the core part of the UI, or the core struct. So everything here will kind of remind you of how things work in a web browser. So you'll see similar names here. For example, I have this display property, and we have display auto, display block, display flex, display inline, display none. These are all concepts from that you'll recognize from the web as well. We have overflow, auto, hidden scroll, text align, left, center, vertical align, auto, middle. Yeah, you get the idea. I also have a simple flexbox implementation. And here is the main style struct. So we have background color, foreground color, size, size min, size percent, size max, fit content, display property, flex direction, flex align, vertical align, justify content, align items. Yeah, basically all of the things you'd see in a browser. I do have some of my own properties here as well that doesn't exist in a browser, just to make things a bit more easier for me. For example, I have a boolean for drop shadows. Originally, when I wrote this UI system, you could actually give it CSS strings. You could actually write actual CSS, because I wrote a CSS parser as well. And I also implemented a HTML parser, so you could write the UI using HTML and CSS. But then I rewrote the entire thing, and I removed that feature because I realized it was more... it was a bit annoying to use that, because in order to, for example, make animations, I would have to implement like a scripting language like JavaScript or something. Or not animations, but like being able to click on elements and such. And I didn't want to implement a scripting language just for doing that. So I just removed all of that HTML parsing and CSS parsing, and I just kept everything in structs instead. However, I do have a scripting language in the engine now. I might show you that later. And here you see uElement config. This is a sort of architecture thing that I'm using in my engine all over the place. I'm trying to keep things declarative. So basically every struct has a configuration struct as well. So basically you should be able to describe everything with a config, basically. I don't know how common that pattern is, but it's something that I decided to use. And here's the actual UI element struct. It has a bunch of stuff to it. And here's some functions. It's probably more interesting if we go to the UI here and look at the implementation. So we have, for example, if we go to let's see if we can get the position algorithm code here somewhere. I think it's called align. There we go. So this is the main function that aligns items, and it basically it has different implementations depending on what properties the element has. For example, if it is if the parent is of type display flex, it will jump to this function here, and it will align it in a flex manner. And here's one for align absolute. So I have a lot of different functions here depending on what properties the element has. But it's going to take a long time to go through all of that. But let me show you, for example, how how I implemented a button, for example. And here you'll see the declarative part that I mentioned. So, for example, to create a button, I just call the function that creates a UI element, and I pass in a configuration struct that explains how this button should look and how it should behave. I can also give it a onClick callback and a style configuration. And we also have the list that you saw where I could spawn things. So here's the list implementation. It's doing the same thing. It constructs a list using different pieces of elements. So here's the actual list element. Here's a scroll bar, some wrapper, and here's each list item inside of the list. And we also have a window element. Here's the bar above the window, and it has some children. So it has a text children here. It has a button children, close for closing the window, and it has an onClick callback. And if I go to that function, here's what happens when I click the close button. It's just calling another function to close the window, basically. So yeah, that's how the UI works. It's nothing fancy. It has a lot of problems, but it does the job for me. Let me move the camera again. And next up, maybe look at the physics things. So the core part of the physics, or what's making everything work the way it does, is the intersection algorithms. Algorithms to detect if two objects or two shapes are intersecting. And I have two different intersection algorithms in my engine. So if I open up the physics here and go to intersection, we have, actually I have three intersection algorithms, but the octree one here is using the Gilbert intersection algorithm. But the two main intersection algorithms is the Gilbert, which is actually known as GJK, the GJK algorithm, and I have the separating axis theorem algorithm. And the physics engine decides what algorithm to use based on the shape that's coming in, because the more accurate intersection algorithm is the Gilbert one, but it's also the more expensive algorithm. Whereas separating axis theorem algorithm is cheaper, it's quicker to run, but it doesn't produce as accurate information as Gilbert. So for an intersection event, you want some information to be able to respond to that event. So you want the penetration depth, like how much the two shapes are intersecting, and you want to know the normal of the intersection so that you can push the objects away from each other. And for doing stuff like rotation, you also want to know the intersection points, like the point on each object where the intersection was. Because the way you apply angular velocity later is to use the cross product between the inertia tensor and the point of the contact point, and you calculate the angular velocity based on that. So for the Gilbert, it actually has two parts. So we have the Gilbert algorithm and the expanding polytype algorithm. So the Gilbert algorithm, actually let's go to the implementation. The Gilbert algorithm simply gives me a Boolean saying if the two objects are intersecting or not. And what the expanding polytype algorithm is doing is taking the data from the Gilbert result, and then it calculates the normal, the depth, the penetration depth, and the points of intersection. And it's actually quite complicated, but what the Gilbert algorithm here is doing is that it's basically it's producing a simplex shape. It takes in all of the vertices from both objects that I want to check for intersection, and it produces a simplex shape that later gets passed to the expanding polytype algorithm to compute the actual data that I want from the intersection, if there was an intersection. So you can see here, first it produces a line defining the shape, and then a triangle, and then a tetrahedron, I think it's pronounced, from the previous lines and triangles. And eventually, if we're able to produce a tetrahedron, we return, we give the simplex to the expanding polytype algorithm, and then the expanding polytype algorithm does some really complicated stuff here. Let me just do like that. So what it does is that it, let's go down here. So it takes in the simplex, as mentioned, but also the two colliders with their vertices. And then it just, it has a maximum number of iterations it can do through to find the convergent of these two shapes. And then I have like a tolerance that checks if the convergence is less enough, then I accept that as a contribution or a candidate to the final results. It's really complicated. I don't think I'm gonna be able to explain it here in this video. But yeah, that's the intersection algorithms that I'm using. And then we also have the actual response logic here that actually is using the results from these two intersection algorithms. So for example, here we're responding to, we're taking the normal of the intersection, the separated velocity, and we compute a dot product between the separating velocity and the normal. And then we just compute a response based on that dot product, basically. And it has a lot of logic here for friction and angular impulses as well. It's doing a lot of stuff here. And one problem with Gilbert and the expanding polytype algorithms is that they are very sensitive to floating point precisions. So that's why you're seeing a lot of like vector 3's dangerous checks here. It basically checks if I've accidentally produced a vector that is infinite or not a number and stuff like that. Because those things actually do happen. but it's not very common, but they do happen. And if they do happen, I just bail out from the response, basically. And sometimes the algorithms produces wrong results because, as I said, they're very sensitive to floating point precision. So here I'm basically just checking if I'm trying to estimate if I've got a wrong result, and I try to fix, to calm down the results a little bit, basically. So that's the physics. I'm not going to go through everything in depth. I'm just skimming over it a little bit. Yeah, then we also have scripting support. Let me actually show you that. So we can do, here's the sandbox project. That's the demo you saw running before. I think I have a share thing here. So let's just do if one. So here's a 3D model of a share, and I've attached a script to it called share.js, and it's actually a scripting language that I created. I can show you that script here, share.js. So it kind of looks like JavaScript. It's a mix between JavaScript and GLSL, actually, because you can do things like function, I don't know, do something vec3a is equal to vec3, 3b is equal to vec3, random return dot ab. Like, it has all of these functions that GLSL has as well. So I can do a c is equal to mix a b. Yeah, you get the point. So here's the script for a share, and what this script is doing is making it possible to sit on a share, basically. This is just a test, it's not perfect, but let me show you that. So if we run this demo now, we should see a share, and I should be able to sit on that share because of this script. So there it is. And if I press E on it, now I'm sitting in the share. It doesn't look like that, but I can't actually move now because I'm in the share. And I can get off the share if I want to. So yeah, that was just a test to see if the scripting engine was working. And there was a bug, by the way. Sometimes objects fall through the ground and stuff because my section algorithms aren't perfect. They do produce wrong results sometimes. However, usually I know the solution for it. In this case, sometimes objects are made of multiple meshes, and if that's the case, my intersection algorithms doesn't produce very good results because it doesn't take that into account, basically. So yeah, that's some scripting. And you may have also noticed the audio that's being played in the engine. And I actually also wrote a custom 3D audio engine for this. So let me actually show you that. It's in a separate project. By the way, both the scripting language and the audio engine is open source on GitHub, so I'll put links to them in the description. But here's the audio engine. It's called AKit, short for Audio Kit. Couldn't come up with a better name. And it's actually very simple. It's using the ALSA sound library to play the audio. And then I have some logic here in, let's see, where is it? I think it's audio, no, sound. So this compute gain function here tries to estimate where the sounds are coming from. so that you can get like stereo audio. So if you hear someone shooting a gun like to the right of you, you should hear it more pronounced in the right ear. I don't know if you've. I remember back in the days there used to be these videos on YouTube. Like I think they were called like binaural uh, barbershop or something, where you had your earphones on and they would play an audio of a barber cutting your hair, and you could sort of hear the razor machine in stereo. So it's sort of what's going on here. So what it's doing is when you initialize the audio engine, you can you specify where the listener is in 3D space, and where the sounds are coming from, and the audio engine will just take care of the math for you and compute the math to rotate the audio in stereo, basically. So where I'm doing that in the engine here is if I go to primitive scene, I think it's update, set listener. Yeah. So here I have a function that updates all the cameras in the scene. And I do a check to see if the camera is the viewer, because I do have support for multiple cameras. For example, I have NPCs in the game and they have their own cameras, so that you can sort of play as an what do you call it? Like in Counter-Strike, when you're not an inspector, but you're watching it from the NPC's point of view. I don't remember the word for it. It's not inspector, but kind of sounds similar. I don't remember. But yeah, so here I'm setting the listener, and I'm telling the audio engine that the direction of where the listener is looking at, and what the up direction is, and where the position of the listener is. And then using this information, the audio engine is, let's see, using the listener here. For example, it's using the forward vector here to compute some information to calculate where the audio should be coming from. And the audio engine also has support for like plugins. I don't know if you've done any music productions, if you're used like Ableton or FL Studio or any DAW like that. You can have something called VST plugins that you can put on a track to apply effects to the audio. I have the same concept here. So I have you can write plugins. So here I have a reverb plugin that produces reverb. And I have this track structure here that has a list of a buffer of plugins, and you can just push how many plugins you want onto the track. And all of the clips on that track will be affected by that plugin, basically. So that's the audio engine. Yeah, and then we have the ray tracer stuff. So here's the core part of the ray tracer. It's the BVH. Without the BVH, I wouldn't be able to do ray tracing. It would be really laggy. And yeah, I think this is too much code to show here, but what a BVH is, yeah, you can look it up on the internet. It just splits the scene into different sections so that you can discard, so that you don't have to loop through all of the triangles when you do ray tracing. And sorry, the actual ray tracing is being done on the GPU in a compute shader. So if I go to shaders, we have this trace.glsl, which is doing the actual ray tracing. So we have this ray cost here, which is defined here, I think. So here you can see it calls traverse BVH, which is here. So here's just a function that goes through the BVH tree and performs ray triangle intersection, basically. And that's how I did the ray traced shadows that you saw in earlier. Then we also have PBR, physics-based rendering. I actually have multiple implementations of this. First, I have PBR.glsl, PBR2.glsl, PBR3.glsl, and PBRnext.glsl. And PBRnext is the one that I'm actually using now. I'm going to delete these other ones. It's because I tried implementing PBR like 5 times, but I didn't like the result of the previous implementations. So, and also I didn't like the way I structured my code in those, so I just rewrote everything a bunch of times. And the PBR next is the one that I'm actually happy with at the moment. And yeah, there's a lot of stuff going on here as well. Maybe that's for another video. Then we also have the actual deferred rendering stuff. Here's where I do the like the water effect and stuff like that. So for example, here I have if I hit something transparent, if it's water, then I call a function for water color computation. And this one actually also modifies this UV offset vector here that I later use to access the texture coordinates for whatever's behind the water, so that I can distort it to simulate like refractions and stuff like that. Later I would probably use ray tracing for refractions, but at the moment my ray tracer isn't fast enough for doing anything serious with it. As you saw with the shadows, they are sort of laggy. It doesn't really affect, it's not laggy in a sense that I get low frame rate, it's just that the bottleneck here is actually the reconstruction of the BVH tree, because it takes too long to construct the BVH. The ray tracer will not do any ray tracing until the BVH is reconstructed. One way to solve this issue is to, instead of reconstruct the entire BVH, I could resize it, but it has some problems. That implementation has some problems as well, so I'm just putting that on hold for a bit until I figure out a good solution for that. Is there anything else interesting to show? Nothing I can think of right now, I think. I can show you, maybe if we go here, I have a bunch of different scenes here to use. We could do scene with terrain. I don't know if that still works. I've been doing a lot of modifications, so maybe I've broken something. But this should give us a randomly generated terrain, hopefully. Yeah, so the shadow mapping doesn't work very good for this. So let's turn that off. But here's some randomly generated terrain. It's just made from using a bunch of different noise functions. let's go back to, or actually you probably want to see this thing. So I reverse engineered the way Half-Life 1 stores their maps. So I made a parser that can convert Half-Life and Counter-Strike 1.6 maps to GLTF. So hopefully we should see a Dust 2 map here now. And what you're seeing there in the console is that it's creating an octree over the entire map to be able to do collision detection on it. It's not perfect, but it kind of works. So here's the Dust 2. You can see I can kind of walk around here, but it's very buggy, to be honest. It's pretty cool. Maybe we can try ray tracing this. Let's turn off shadow mapping. Turn on rays. Oh, it actually does work. So here's the dust map ray traced. You can actually see some real-time shadows here. Now it's only ray tracing the shadows. It doesn't do, at the moment it doesn't ray trace colors or anything like that. It's just shadows. And in this particular case, I actually think that the shadow mapping looked better. But of course, now we're not getting real-time shadows. So that's the Dust 2. I can load any Half-Life 1 map or Counter-Strike 1.6 map if I want to. Let's also maybe show you the NPCs. So if I do AI human, let's do maybe that. Hopefully it's gonna work. I'm not sure. Yeah, something is a bit messed up, but it kind of works, I guess. And I can actually inspect what they are seeing. So now I'm viewing I'm not controlling anything. We're viewing it from the NPC's point of view. Can change NPC. And now we're back to my point of view. I don't know why the animation is bugged out, but it is. Yeah, I also have this thing, which should be Gordon Freeman from Half-Life 1. reviewing it from the NPCs point of view. And it's actually a really stupid AI. It's just making up decisions based on noise, basically. Yeah, so they're receiving some noise from noise functions and decides what to do based on the noise. So yeah, that's basically it, I think. I hope you enjoyed this video. And by the way, if you have any questions for the Q&A video that will be coming up, have a look in the community section of YouTube. I made a post there where you can make comments for questions. Or you could also post the questions in a comment below this video, and I will include that in the Q&A video as well. So thank you so much for watching, and I'll see you.